I just want to look at the mechanism of the hydration of a carbon-carbon double bond using acid and water. It's a hydration because we are adding water over the double bond. And the mechanism is going to be as follows. It's important to recognize that the H2SO4 that we're using here could have been any acid. And sometimes we might have just written this reaction with an H plus over there to indicate that the acid is acting as a catalyst. And we should recognize that. So we can write there cat for catalyst. So what is happening in this reaction? How will we show a mechanism of this? Well, we understand that the first step is always, like with the addition of HBr over a double bond, is the protonation of the double bond with the acid catalyst. And at this stage, we now should know and recognize how these are going to happen. We can draw this curly arrow, which shows that the pi electrons are going to add to the H+. The product of that is going to be a carbocation, and our options for the carbocation, so the H is added to one of those carbons, the carbocation is going to form to give the most stable one. We would either have a primary carbocation here or a secondary carbocation forming there. And so the secondary is more favored. So in this mechanism, we will have a secondary carbocation there. Now, in the addition of HBr over a double bond, the next thing was the nucleophile came in, which was the Br minus. In this case, we don't have Br minus, and it's a poor nucleophile, but we've got water, which is a good nucleophile. Just out of interest, the SO4 that was formed as well, because as we picked up this proton came from H2SO4, that means that we have something that looks like this. If one of the H's were taken up, we've got an O minus like that. It's important to realize that this is, whilst in theory it can act as a nucleophile, it's a very, very poor nucleophile because this minus that's over here is very stabilized into the sulfur double bond oxygens that we have here. That's indeed why you can draw out these resonance structures, but it's actually why H2SO4 is such a great acid, is because this negative charge, the conjugate base of it, is very stabilized through resonance. So you can do that as practice. So we don't have to worry about this as being a nucleophile. The water is going to be a nucleophile, and it can do that because it's got these lone pairs of electrons which it can donate to the carbocation. So this intermediate is our carbocation, and we should label these when we do our mechanisms, and also recognize that it's more than just a carbocation, it's a secondary carbocation. All right, so the water is giving its electrons to this carbon, and so that arrow push is showing what a new bond is going to form. All right, a new bond between the OH2, and so that's going to be positively charged over there. For the next step, this intermediate, by the way, is called an oxonium, and we should know that as well and make sure that we do that, write that down. A positively charged oxygen. For the next step, it's actually going to be useful to erase this OH2 and rather draw it in specifically, one of the H's, because we need to show that it's now going to leave. I should have drawn an arrow there showing this reaction. We're going to remove this proton, and the electrons between this oxygen and proton are going to be given back to the oxygen atom over here. That is how it's going to be made neutral. And so this proton needs to leave. What's going to pick it up? Well, there's water in the system, OH2, which can pick up that and become H3O plus, and our product OH2 is, alcohol OH is going to be there like that. All right, so, and plus H3O plus. So now we have our H plus again over here, which can go back into the reaction over there, and we can add water, come back through here, H plus gets recycled again. And so by looking at this overall mechanism, we can see that the acid is in fact just a catalyst in this reaction. It's not being used up in the reaction, it's being regenerated at the end, and so it's catalytic. Overall, it's a hydration. I don't like drawing it that way, but it's kind of like, because if we put that H in, we should draw all the other H's. So but that H over there and the OH come from the water over there. All right, that's how it was added. A word of caution here. For some reason, I'm not sure where this is picked up from, but I see this all the time, that when we do this reaction, notice that it is water that is acting as the nucleophile. There is a great tendency, and please, if you are thinking of doing this or you're doing this at the moment, please stop it, to sort of show that H2O suddenly becomes H plus and OH minus. I see this every year, and then people use the H plus to do the first thing, and then the next thing they use the OH minus as a nucleophile to come in. This is simply not true, all right? This is complete hogwash. Don't do it like this. If water could split up into H plus and OH minus spontaneously, then we could not exist, all right? It's impossible. So please don't do this. This reaction is using acid. It's under acidic conditions. It means we mustn't have any OH minus present. Right. If you took an OH minus, sodium hydroxide, and mixed it with acid, you would get water. This reaction does not happen like that. Okay. It's not great. All right, so that's the hydration of water. It's following, the hydration of this molecule. It's following Markovnikov's rule because the most stable carbocation is being formed, and so the major product is the one where the most stable carbocation was being formed. You should practice this. So in order to practice it, let me draw out pretty much exactly the same sort of molecule, but I'm going to put the double bond in that position. So work out what the product of this would be if I'm using H plus and H2O. All right, so now I just said H plus instead of H2SO4, but it's the same thing. All right.